All right. So, we are here for our exam, my exam three. Um, so, for this one, we're going to kind of be explaining uh, a phenomena that happens between diffusivity and heat. Uh, so, the situation is there are, well, in general, when you have a liquid, for this instance, we'll be saying water. When you have water uh, that has an equal temperature as the ambient air, uh, you'll find that the temperature of the water can continue to drop because that water will can continue to drop if the air is not saturated with water. Um, because the water will diffuse into the air, therefore calling it to cool down. Um, yes, and so I'm gonna kind of go into that, and so we're gonna start off with our Lewis relation here. Um, let's see, we call it A1. Ooh. Um, Not yellow. Our Lewis relations, and so for our Lewis relation, what we'll be using is our Nusselt number and our Sherwood number. And so these two are going to be equated to a couple different equations. So our Nusselt number in U is making those in U and not in A. It's going to be equal to our heat transfer coefficient times our distance all over our thermal diffusivity, which is K. And then our Sherwood number is going to be equal to our mass transfer coefficient, which is Kc, times our distance. And that's all going to be our mass diffusivity. Our mass diffusivity. And so as we continue here, as we found in our previous exam, our Sherwood number is also equal to A times our Reynolds number to the B power times our Schmidt number to the C power. And then conversely, or also, our Nusselt number has a similar equation in that if you were to work this out in terms of heat, you will find that our A times our Reynolds number to the B power times our, in this case, it'll be our Reynolds number, Reynolds number to the C power. And you'll find that these two will be equal. And then lastly, we know that our kinetic viscosity, kinetic viscosity, I'm just gonna draw V because I can't do the curvy V. It's gonna be equal to our thermal diffusivity up here. So it'll be A. And down here it'll be our kinetic viscosity is gonna be equal to our, I'm gonna make this K. It's gonna be equal to our mass diffusivity, so DAB. And so from here, we are going to divide our Nusselt number by our Sherwood number. And so what is that going to create from these? We're going to have these are going to cancel out. Let's see, we're going to have these will cancel out. And then we'll find that these will cancel out. As we go through each of these equations and divide them, we'll have our heat transfer coefficient times our mass diffusivity all over our thermal conductivity. Thermal conductivity and thermal diffusivity kind of interchangeable. in this case, they'll be interchangeable. And our mass transfer coefficient. And then we'll find that they're also equal to our Prandtl number to C power over our Schmidt number to the C power, and our DAB over our mass diffusivity coefficient over our heat conductivity. I'm gonna be bouncing between those. I am going to set it as thermal diffusivity. That's what we'll stick to. And so from there, these are all equal to 1 over the Lewis number. Let's keep that in mind, because we'll be coming back to that. And so what we want to focus on is I'll just copy and paste actually. This, I'm going to bring this down, bring this equation is, since these are all equal to the where's my pointer? The Lewis number here, we can set these equal. So and that is equal to this. And so what are we going to do from here? So we're going to see if we can cancel some things out. So real quick, I'm going to go back and change these. Change this to an A, like I had in the beginning. So we don't get these two confused. All right, and so from there, we know that our thermal diffusivity here is equal to rho, our density, times our specific heat over our K. And so we're going to plug that in for A. I blanked. Let's see. I'm going to DAB over K, which will equal RK rho CP. Apologies, these are actually flipped. This will be K over rho CP, and thus this will be K over rho CP. And that would instead make CP up here over our K. And so we're going to plug those back in over here. So this is actually equal to our density times our specific heat times DAB over our K. And so what are we gonna notice here? We notice that we can cancel some things out. Specifically, these two are our K and DAB are in both equations, so they will cancel out, and that'll leave us with our heat transfer coefficient over our mass transfer coefficient is equal to our density times our specific heat. And we'll find that this is our Lewis relation. And so the significance of this is, as I said, we were trying to define a problem where water evaporates to the air due to the air not being saturated. And so here we see a relation between uh, our mass transfer and our heat transfer, and that's related to our uh, density times our specific heat, so our volumetric specific heat, um, and that'll be important later. So we'll define that. We'll show the importance of that later. All right, now we're moving on to our next section here. And so for this one, we need to uh, see how the mass balance compares to our heat balance. And so for here to go into it, we have for our mass side, we have our mass transfer coefficient is multiplied by our concentration. So this is, again, we have water evaporating into air. So we have two concentrations, concentration of water and concentration of water at the surface, and then we have concentration of water in the air. And for here to have the a positive number, we're going to use the concentration of water first. So concentration of water at the surface, CS, minus concentration of water in the air, which concentration of water of air is assumed to be less than at the surface in order for this to happen. That's going to be equal to our heat transfer coefficient times the temperature. So as I said earlier, the temperature of the surface, temperature of the water is going to be less because the water is evaporating, and this is going to be cooled. So the temperature of the air is going to be higher. So TA minus our temperature at the surface. And then to relate these two, we have our heat of vaporization. And so from there, we're going to pull down that Lewis relation that we got earlier. And we're going to go ahead and use that. So copy, see, paste. And so we see that we have our, that's okay. So we see that we have our equation here, and we see that these two variables we have if we just divide this over. So I'm going to go ahead and do that. CA equals H over C, and that's just going to be H over KC. Wow. H over KC is just going to become rho times our specific heat. All right, and then from there, we want to break this down a little bit. We know that concentration is equal to the partial pressure over RT, and so for this one's going to be partial pressure of water at the surface. So it's our saturation. At surface is going to be the most saturated, so we're just going to continue to call it PS. And PA, and that's all going to be over our RT. And then we have our density is going to be equal to our total pressure over RT, and so it's going to be P tot over RT. I'm just write it out. TS, and so from there, we know this is going to cancel out because it will be dragged over there. And we'll be left with our heat of vaporization times PS, PA equals P tot times CP, TA minus TS. And so from here, we need to find our relative humidity, and so our relative humidity is going to equal our partial pressure of water in the air, so our PA, and it's going to be over RPS. Now, there's a lot that goes into this with our Antoine's equation, but to kind of think about it more practically, is that the partial pressure of water at the surface is going to be our max, because that's at the surface is going to be where it's most saturated, and so that's going to be our max. And so the partial pressure of water in the air is going to be compared to that, because that's going to be the max. So it's going to be partial pressure of water in the air, our PA, over our partial pressure of water at saturation, our PS. In this portion of our exam, we are going to be explaining the relationship between the adiabatic saturation temperature and the wet bulb temperature. And we're going to find that they are very closely related. So for our situation here, let's see, we have progressed very far in our technology, so much so that we have a tube, a infinitely long tube. Okay, this tube has some water sitting at the bottom. Go add a color here. Got some water in there, and then we have our air flowing in. Okay, and so with that, we have the mass of our air flowing in. All right, I think that's the best I'm gonna get. So we have our air flow. We have some mass of our air flowing in. We have the temperature of the air going in, and then we have the partial pressure of water and air going in, and then going out, we have our temperature going out, which will be different again because the water will be evaporating into the air, so the temperature will not be the same. And we have partial pressure of water and air at 0.2. And so from what we discussed earlier, we know that partial pressure of, well, not from what we discussed earlier, but because this tube is infinitely long, eventually, as it approaches infinity, partial pressure of water and air is going to equal the partial pressure of saturation. It's going to be saturated. And so that's going to be partial pressure of saturation at the surface. So it's going to equal PS. And so from here, we are going to analyze the enthalpies. So we have our enthalpy going in, okay? So the equation for enthalpy is up here. Q equals MC delta T. So we have our mass of air going in times our CP, our specific heat, delta T. So again, because this is enthalpy going in, let me make sure I clarify that. So enthalpy going in, let me rewrite this. This enthalpy going in, our temperature, this is just for our temperature going in. And so the delta T at the beginning, it's just going to be the temperature going in. There's going to be no reference temperature. And so it's just T in. And that's going to be plus our heat of vaporization. So we need to account for the evaporation. So our heat of evaporation. And that'll be multiplied by our PA1 over our RT, which we know will give us the concentration here. And we're going to multiply that by our mass of molecular weight of water. And then we're going to multiply that by the reciprocal of our P total times the molecular weight average. And that's just going to give us the amount of water in our system at that particular point. And so we have our enthalpy in there, and now we're going to get our enthalpy out. Excuse my bad handwriting. So our enthalpy out is going to be a very similar equation. So I'm just going to copy and paste this. I'm kind of bothered by how unproportional that line was. But so I'm going to copy and paste this. And our only differences will be our temperature here. So it will be our temperature out. Then our other difference will be our partial pressure. So it will be PS. Yes, and so because this is infinitely long, the enthalpies will eventually be equal to each other. Our enthalpies will eventually, and so our enthalpies will equal each other here because this is a steady state system. So I'm going to copy and paste these. Let me see, I'm gonna decrease the size of that one. And then decrease the size of this one. I'm gonna set those equal to each other. And so we're gonna see that these two will cancel out. Within each equation, we see that the RTs will cancel out. And that's going to leave us with blanking. See our specific heat times our temperature in plus heat of vaporization weight over our total times an average. Equal to our specific heat temperature out plus heat vaporization. All right. And so to kind of, all right, and so we're going to clean these up a little bit. So get everything on one side. We have our lambda, molecular weight of water over our B molecular average. That'll be times our PA minus our PS. And then that'll be equal to CP Tn minus T out. Excuse me, that will be our T out minus T in. And so we're gonna rearrange this a bit. Let's see, we have our equation here. It's just because I was running out of space. We have, I'm gonna have our, let's see, our lambda RPS. How many times are T in minus T out? All right, and so what do you know? This is our wet bulb temperature. And this is our adiabatic saturation temperature, so AS temp. And what we see that the equations are pretty close. They're almost the same. And so from that, we know that the adiabatic saturation temperature and the wet bulb temperature are the same. Yeah. All right, so now we are moving on to our next section here of our exam. Here we'll be working with a cooling tower. And what's going to be happening here is we have our water flowing in from the top, and it'll be falling down and getting cooled by this air. So we have water falling down and it's going out at the bottom, and we have air flowing in through the fan. The fan's going to be pumping air in, and that'll flow out through the top. And so our units here, so for our liquid, is going to be flowing in at kilograms per second. Our gas is going to be flowing in kilograms per second per meter squared, and we'll kind of get back to that, why the meter squared is added in there. And then this is all going to be flowing in the Z direction. Z will be going down. And so we see that we also have a packed area here that we'll be working with. And the area for that will be in terms of meters squared per meter cubed, in terms of our surface area per volume. And so we'll start getting into our equations. So for this one, we need to define our differential equations for this. We need to define our change in mole fraction of water as we go down this column, our change in temperature of water as we go down this column, and then our change in temperature of the air as we go down the column. So we're going to start off with our first equation. Here we're going to see that's going to be the our gas flow rate here over our molecular weight of water, and that's going to be multiplied by our mole fraction, and then we're going to see that that's going to be equal to our mass transfer. So from what we defined earlier, we know our mass transfer is equal to our mass transfer coefficient times our concentration at the surface, which is where our concentration of water is highest, so concentration at the surface, minus our concentration of water in the air. And for this, again, we're working with our packed area here, so we're going to multiply that in. And so we're going to multiply this by a volume. And so to do that, we're going to multiply it by our cross-sectional area times dz. And basically, cross-sectional area is going to be this times our dz. That'll effectively give us a volume to cancel that out. Earlier I said that we have this meter squared here, and And that's in there so that we can add the cross-sectional area to this side too. And the reason that we're going to be doing that is because this cross-sectional area otherwise would just be bouncing around in the equations. And so we kind of want to get rid of that to make this simpler. So effectively, the cross-sectional area here, that will cancel out. So this will go away and then this will go away units wise. So that won't be a problem. But in this equation, these two will go away because they'll cancel out. And to simplify this even more, our flow rate here over our our molecular weight is going to be constant. It's not always necessarily constant, but to simplify this, we're going to say that it's going to be constant. So we're going to take those out. So effectively over here, we'll be left with dy. And we're going to move this dz over. So, wrote dy, I said dy and wrote dz. Our dy, and then over here we're going to have our kc times our concentration at the surface, concentration in the air, multiplied by a over m over g. And so what we know from earlier is that these can be broken down into P over RT, partial pressure over our RT. And so it's going to be Kc, partial pressure at the surface over RT, and partial pressure in the air over RT. Now, that can be broken down even more, this partial pressure in the air, but it's not really necessary because it's going to go away here soon anyway. And so bring that on down. And so effectively, this whole portion is going to, I'm sorry, somebody's blowing on my phone. It's going to be equal to the molecular, the mole will be equal to our mole flux of water. So we can simplify that out to equal y over dz equals our mole flux times a m g. All right, and then we'll move on to our next equation. All right, so for our next portion here, earlier we found our change of our mole fraction of water in terms of height. And so next we're going to consider our change in our temperature of water in terms of height. And so whenever we think about the temperature, we think about also enthalpy, the energy of that. And so we're going to write out d h, the enthalpy, and it's going to be enthalpy of water, so we're just going to add that in. And we know that enthalpy equals Q equals mc delta T, so we're going to have our flow here. And just like we did with the gas flow earlier, we're going to multiply it by A so that we can cancel that out later. And that's going to be multiplied by our specific heat, so specific heat of water, and our delta T. And so when we think about the heat of the water here, we have the heat that the water gains from the air, and then we have the heat that the water will be losing through evaporation. And so when we think about the heat that the water gains, we have our heat transfer coefficient that's going to be multiplied by the temperature of the air minus temperature at the surface. And we have to consider our packing here. So it's going to be multiplied by A. And whenever we have lowercase a, we're going to have to multiply it by the cross-sectional area times dz to make it our volume. And then we're going to subtract that by the evaporation. So when we think about evaporation, we're going to have the heat of vaporization here. And that's going to be multiplied by our molar flux, because that's what's driving this evaporation. And again, this is for our packing area, and so we're going to multiply by a lowercase a dz. And so from here, again, we can cancel all these areas out, cross-sectional areas out. We're going to move dz over here, so we're going to have d tw over dz. And we can take out, take out our area. I'm going to have our flow and specific heat. That's going to be multiplied over here. And that's going to leave us with our heat transfer times our temperatures, minus our heat of vaporization times our flux, our molar flux. And so there goes our equation for our change of temperature in terms of height. All right, so for our last equation, we found the change in mole fraction of water. We found the change in temperature of water. Now we need to try and find the change in temperature of the air. So for this, we're going to be working with enthalpies again, and we're going to break this out. So one thing about this system that was important to know, we have our air going in, water going in, TW, and our air going in. And thus, because of that, this is an important thing that we're given, is that this system is steady state, which will mean that the change in enthalpies here will be equal to 0. And so, because they're counterflow set up here, we'll do TA minus TW, and the change of those is equal to 0. And thus, temperature of those are equal to each other. So this is important because we just found the change in temperature of water earlier, and now we just need to define the temperature of air, and then break that down, and then find our dTA dz. And so again, excuse me, this is enthalpy, not temperature. Enthalpy. If it was that easy, it would have been nice, but this is our enthalpy. And so we know our enthalpy of water, and so we just need to find our enthalpy of air and then use that to find our temperature of air. So for the enthalpy of air, two things we need to consider. We need to consider the heat that air already has, and then heat that it'll be taking on from the water. And so for that, we have our Q again equals MC delta T. So we have our gas times our cross-sectional area, as we have been doing, times our specific heat of gas. Did I find that as CA or C? What did I make that? CA. I think I made that CA. So I'm gonna call it CA because specific heat of air. And then times our temperature. Um, and then that's going to be added to our the heat that we're given from the water. And so from that, we'll have our G over molecular weight of water, as we did earlier, and that's times our mole fraction of water. And this is to give us our water content in the air. And then that'll be times our heat of vaporization to give the heat from the vaporized water. And then again, that'll be multiplied by A. And so all of that will be, move this over a bit, differential here. And so we can set that equal to the change in enthalpy of water that we have up here. So we're going to bring that down. And we're going to set that equal to this equation. And so from there, off the bat, we already know that A is going to cancel out, as we've just been doing this whole time. And from there, we again were given that this is a steady state. So we can say that our mass flow rate, our G, our specific heat, and this whole coefficient, if you will be constant. And so we'll have a times our change in temperature, plus our lambda here, over m times change in mole fraction. Again, because this whole thing will be constant, because it's a steady state. Now it'll be multiplied by this again. I'll actually rewrite it. I'll come back to that one. But we can see that, well, actually, I'll just rewrite it. But as I rewrite this, we can see that I'm going to go ahead and move these DZs over right now, divide them over for our use here. Because now we have our DT DZ, and we know our change in mole fraction, and so we can plug that in later on. And so coming up here, as we found earlier, we're going to copy and paste this. And so we see that this is equal to dy dz. And so from there, we know that this, we see m over g here, so that'll cancel out. And we see our a times nw, and so these will cancel out. So what we'll be left with is our dt, our change in temperature of air, times dz is equal to, we're going to move this over to equal to our area times our heat transfer coefficient, over our mass flow rate of air, our specific heat of air, um, and as times our temperature of air minus our temperature at the surface. And we found our equation here, and what we're going to do next is we're going to use Python to solve these differential equations. All right, so we are now moving on to the coding section of this exam. So here, I've typed in most of our parameters, most of our givens, um, and I'll kind of go through some of the calculated ones. So up here, you can see I've already imported our tools. We'll be using NumPy, and we'll be doing some solvers down here later on, and we're also going to be making a graph. So that's what those tools are going to be doing later on. I have all of our non-calculated givens here. So I have our heat transfer coefficient, our R value, our gas constant, um, our density of our air here. We have the specific heats here. We have our heat of vaporization here. Um, we have our specific area, um, and then our molecular weights here. This is of water and this is of air. Uh, oh, to go back to that, this is specific heat of water in gas form. This is water in liquid form. Um, and then we have our velocity. This is the velocity of air specifically. And then this is our liquid mass flow rate, and this is our pressure of um, uh, the cooling tower, the pressure in the cooling tower. And so what I'm going to add on to here, we need to have, I'm going to come back down here, but we need to have our mass transfer coefficient, which is going to be equal to um, our heat transfer coefficient that we defined earlier, divided by our the density of our air. And that's going to be multiplied by the specific heat of air. All right. And then also, uh, one thing that I'm going to also add is our zplot variable. This will be coming in to play later on. This will be coming into play later on. So that one space is going to be from 0 to height. Let's see. Yeah. So, and we're going to call in 21 equally spaced values. And so from here, what we need to do is we need to come back up here, and create a calculation for that will give us our partial pressure based off of our temperature. And so we're going to define that as PV function of our temperature. And then I'm going to come over here. It's going to return. Make sure I don't miss anything. 10 to the power of 8. 73 divided by 230.426 plus our conversion from Kelvin, so minus 73.15. For this one, I didn't factor in the 0.15, so I'm not going to put that in the conversion. And then going to be divided by 760, and I would for this part, because this is for the pressure, I would just put our pressure down here, but our pressure variable, but at the time it has technically not been defined yet, so that won't work. So I have to actually type it out up here. So go ahead and run that. Let's see. All right. So now we can go ahead and find our molar fraction of air, and then we can find also the mass flow of air. So it's going to be the molecular fraction, mole fraction, let's see, call that N, is going to be equal to 0.5 times P of our temperature of our feed in, our temperature in. So I'm gonna multiply that in, and then that's going to be divided by our pressure. And so with that, now we can find our mass flow in. And so that's going to be equal to let's see, mass flow in it's going to be equal to our pressure times our molecular weight of air, and that's going to be divided by RT. So here that's going to be R times our temperature of air in, and that's going to be multiplied by our velocity. All right. And then lastly, because we're going to be doing an IVP problem, initial value problem, we need to have our initial value guesses. And so we're going to have an initial value guess for our exits, so our mole fraction of air exiting, and then our temperature of air exiting. And so for our mole fraction of air exiting, we're going to call that out, and we're going to set that equal to we're going to make it a guess. I'm going to make sure I make it a guess. Underscore G. And that's going to be equal to, we're going to set it equal to our feed in times 1.1, because it's going to gain a little bit because it's going to be interacting with water, and so we're going to factor that in. It's going to be our what did I define that as? Our feed in times 1.1, and then for our temperature of air out, let's go and guess. We're going to think that that's also going to gain a bit. So our guess for that is going to be our TA in, temperature in, plus 5. We'll go with that. And then I'm going to make sure to define this. We're going to put solution equal to none. And we'll see why that's important later on. Okay. Just give us an open solution for now to then be used later. All right, so the next thing we're going to do here is define our variables. And so we're going to start this off with by defining, we're going to do all of our formulas at once. And so it's going to be define dy, temperature of water and temperature of gas. And then it's going to be in terms of z and this variables. And so down here, our first variable is going to be our first variable is going to be equal to our y. Our second variable is going to be equal to our temperature of water. All right. And then our third value is going to be equal to our temperature of our gas. All right. And then now we need to calculate some more things. So we need to calculate firstly our flow rate of air in. Currently we have our total flow rate of air. So currently we have just our flow rate of just air, and we need, I should call it our molar flow rate of gas is what we need. Currently we have a molar flow rate, I'm sorry, not molar flow rate, but we have our mass flow rate of air coming in, but that's not accounting for water that evaporates and joins that. And so we need to find that total. And so in order to do that, we first need to find our water vapor, our mass flow of water vapor. So that's going to be equal to GW times our molar fraction divided by 1 minus our molar fraction to get just the water. And then that's going to be multiplied by our air, our flow rate of air, in, and then that's going to be multiplied by and that's going to be multiplied by our molecular weight of water divided by our molecular weight of air. Yeah. All right. And so that's that. And then now we can find that total G. It's going to be equal to our flow rate of water, our vapor flow rate of water, and our flow rate of air. All right. And now next we need to find our total molar fraction. And so that's going to be equal to our G. It's going to be equal to our G divided by each individual part. And so that's going to be our mass flow rate of air divided by the molecular weight of air. And then it's going to be added plus, the gas flow rate of water divided by the molecular weight of water. All right. And then from there, we'll be finding the new specific heat of our gas. And so that's going to be equal to, say, Cg. It's going to be equal to our specific heat of our air. What did I call it? Up here. Okay, I call this here. Specific heat of our air times our mass flow rate. So it's going to be, and then that's going to be added by our specific heat of water. Did I call it CW? CWG. Multiplied by our mass flow rate of water. And then that's going to be divided by our gas. All right. And so now we need to define our molar molar flux variable, because we need to use that in our equation. And so that's going to be equal to call that NA, NW actually, of water. It's going to be equal to our mass transfer coefficient divided by our R divided by our temperature of gas times what's it multiplied by? Times our partial pressure of TW minus our molecular weight times our total pressure here. And so we're going to use that to then finally define each of these equations that we're going to be doing. And so we found the equations that we found earlier, the three differential equations that we found earlier. We'll now be putting those in, and so that'll be negative A times M divided by G times our mass flow rate, and that is our change in mole fraction of water. And so next we're going to do our change in temperature of water. So it's going to be dTW is equal to A divided by L CW. What did I find that? CWL. Times R H heat of vaporization. I call it lambda. I'll call this lamb. Multiplied by our mass flux, molar flux. Excuse me. All right, and then we're going to now do our changing our temperature of gas. So dTg equal to our um, specific area times our heat transfer coefficient divided by gas flow rate divided by specific heat of gas times our temperature of gas minus our temperature of water. And so now that we have those, we're going to set those to return in order. So it's going to be dy dTw. Right. All right. So what we're going to do now is put in our solve IVP function. So it's going to be our solution is going to be equal to solve IVP, and that's going to be our function of dy tw tg. Let's see, and our span is going to be from 0 to our height. All right, and then our initial values are going to be in order our y exit. So I'm going to put y out, our temperature of water out, and then our temperature of gas out. And then I'll come back to the problem that we face with that. And our method is going to be, make sure I come in that. Method is going to be Radu. Method is Radu. It's Radu. I don't know how you correctly pronounce that. And then output is going to be equal true. And then that's it. And we're going to put that as dot sol. I'm going to put z plot for the plot that we're going to make later. And so what problem do we have right now? Well, let me get this TW out. A problem we face right now is we know our TW, but we don't know, we know our temperature of our water, but we don't know the temperature of a gas and our molar fraction out. They don't have a guess to converge to. And so what we're going to do is we're going to give them something to converge to. And so we're going to tab all this over. And then put this over. And it's going to be fine. Converge. Let's go our feed. we're going to put it in terms of v2, this variable, a second variable. Keep it simple. And our y out is just going to be equal to our first variable in this matrix. So it's going to be equal to v2 and then our temperature of our gas out is just going to be equal to the second one. All right. And then from there, we want to return the last value in these matrices. And so we're going to have solution from 0, it's going to be -1, so that we return the last one. And then next we're going to have minus our y. What did I call it earlier? Yn. So that we make sure we pull in our last ones. All right. I'm going to subtract that from our TAN. All right. And so now we're going to run a root root function. And so it's going to be using our function that we used up here. And then we're going to be using our other guesses that we have. So our and our temperature of air out, I guess. So we should be able to run that. Let's see. All right. Yeah. All right, that took some time. But kind of a summary. I kind of had to go through and make some corrections. I had a lot of typos. So I'd say the biggest cause of error for my project on this one has been missing tabs or typos. But yeah. All right, so for our last portion of the exam, we're going to be making our plots. So for this, we're just going to go ahead and type in fig equal to make, let's go to subplots. Rows is equal to 3. And our columns are equal to 1. And then we're gonna start off with our first line. So this one is gonna be for the change in y, the change in the mole fraction of water. And so we're gonna do fig, add, scatter. I'm gonna do x equal to our z plot that we did earlier. And our y is going to be equal to sol 1, not colon, and the colon is to just call the whole row. All right, and then we're going to call that going to call that our water. So I'm going to call it let's see, y of water, and then our row here is going to equal 1. And our column, that's not what I'm saying. And our column is going to equal 1 as well. And so we're going to repeat this for our temperature of our water and our temperature of our gas. So because of that, we can just copy and paste this. So we're going to, this is a problem. I'm going to copy and paste 3 times. So this one is going to be our temperature of water. This is going to be our temperature of our gas, TG. And thus this is going to in order to separate these, I'm going to change these to 2. This is going to be column, row 2. That's what the row is to separate them. And this will be row 3. And then we're going to go ahead and run that. Let's see. Make sure these are all run. Change it to lowercase x. Oops. It's supposed to be our 0 index here. It's supposed to be from 0 to 1. I mean to 2. Since there are 3 indexes. And there we go. There are our plots.